Okay, welcome everyone to the weekly colloquium of the School of Astrophysics. As some of you may know, this is the 100th colloquium. And so let me tell you a little bit about the colloquium series. So, School of Astrophysics formally started in May 2022, and our first speaker was one of our former students, and that was in July 2020. So from there, we roughly have about 30 talks per year. And so after about 3.5 years, we are now at the 100 mark. And to celebrate that, we have invited, we are very glad to have Professor Tarun Souradeep as the speaker today. And the colloquium has been a very integral part of the academic life of School of Astrophysics. And of course, physics department, the weekly colloquium is going on from 2012. And historically, many former students have reported that they have learned a large amount of astrophysics and the sociology of astronomers from the colloquium and interaction with speakers and so on. So obviously, we need to celebrate the landmarks related to the colloquium series, and that's what we are doing today. So coming to our speaker, Professor Souradeep did his undergrad at IIT Kanpur as a mechanical engineer. But after that, he decided that instead of a revolution per minute of a car engine, he is more interested in the evolution per giga-year of the universe. And so he joined IUCAA, which was very new at the time, as he was actually in the first batch of IUCAA PhD students. There were 3 at the time. And you know that Dr. Souradeep, who is our colleague, was probably in the 12th batch of IUCAA students. So just one era after Professor Souradeep. So after finishing his PhD from IUCAA, he did a couple of postdoctoral stints, one at Kansas State with Bharat Ratna. Incidentally, Bharat Ratna was a speaker a couple of years ago. And then another one at SIGA. And then he came back and became a faculty member at IUCAA. And at IUCAA, when I first went to IUCAA in 2008, I saw that many of the doors are closed, but Professor Souradeep's door was open, and there was this small, I will not say long, but a small queue of students waiting to talk to him. So there are many students who are always working with Professor Souradeep. And I'll come to that. And then after, in 2017, he went to IISER Pune as the head of the physics department. 2019. And then in 2018, 19. 19, okay, 19. And then in 2022, he became the director of Raman Research Institute in Bengaluru. So Professor Souradeep's research interest has been cosmology and gravity, various aspects of cosmology and gravity. He was part of the Planck Cosmic Microwave Background Mission team, and so Planck actually is the mission that measured the cosmic microwave background with the highest precision till date. And as part of the team, he also got the Gruber. He was part of the team that got the Gruber Cosmology Prize. Later, he actually became one of the leaders in India in gravitational wave related observations and gravitational wave science, and he was part of one of the leaders of the team that sort of got the LIGO India project going, and finally in 2023, as some of you know, 2,600 crores was allotted for this project, and he was a co-author in the Nobel Prize winning paper of gravitational wave discovery, and he got the breakthrough prize in fundamental science based on that work. And apart from these honors, he has also got numerous others, and I don't want to list all of them, including the Souradeep Fellowship, and he's also fellows of the different in the National Academy of Science and the Indian Academy of Science, and so on. I would rather mention that to me, Professor Souradeep's legacy, in addition to all the things that I already mentioned, is because of the many students he trained as advisors at different stages and different places in his career. And I think now, if you look at the various Indian institutions and some international institutions, there is at least one student who did their PhD or postdoctoral work with Professor Souradeep. And I think that personally would be, I mean, as part of a teaching institution, I feel, I think the appeal of that legacy is the most to me. So, so he has played to catch quickly after the talk. So without further delay, I will invite Professor Souradeep to deliver the lecture.
Okay. This is on? Okay, great.
Yeah, recording part.
What?
So you have to preferably be there.
Oh, I have to speak in that. Okay, this. Okay, no, that's okay. I can do that. No, I have no problem. Yeah. Okay, great. So let me begin by thanking Presidency University, the School of Astrophysics, for this invitation. And I'm delighted to know this is the 100th colloquium of the newly formed School of Astrophysics, and I wish them long innings, double in times. And, I should say the faculty that you see here, sitting here, I had the privilege of knowing them from very young age. And I was just telling the Vice Chancellor that, this group of people are the kind of, as a whole batch, are internationally competitive, which many of you who are working with them as undergraduates must have realized how important that is when you want to move on and get recognized. So it is certainly a great pleasure, and I, really love talking to students, largely because from around 2009, 10, I mean, I was always interested in mentoring, but I sort of saw the potential of mega science in reaching out to large number of students, and also more importantly students of all types with all different capabilities. These are somewhat different from the research that you normally, expect. I mean, in research institutes, the expectations are people who've done their masters very well, know all the standard textbook very well. To get to these breakthrough things, the kind of people who really may play a big role may not have had that, right? May not have been the best students. In fact, if you go to LIGO US, the guys who are commissioning the detector and working, I mean, some of them are high school graduates who over a decade have become really the experts, right? So education comes in various ways, and one of the ways is to be hands-on. And I think Mega Science Projects provides that to a larger number of people. So that was one thing that I felt, particularly from this very elite group of undergraduates. You should keep that in mind, that there's no one single path to excelling in research. Research means doing something new. Okay, it doesn't matter whether, you knew all the equations before you did it, but you intuitively guessed at the answer. That's also research, right? So that people have come up with things in a very different way, and you should realize, and you should be accommodating that. You should not think, oh man, this is not the right kind of research. There's no color to research. Everything that leads to the final goal of producing new results is research. Okay, so gravitational waves, as I said, I had a different reason to be interested in it. Somehow this picture is not showing up well, but what you see here is a black and white rendition of the LIGO India project that is soon going to come up. It's already been tendered out. Okay, and out there is the Planck satellite, but I'll tell you what I mean by that now. So let me start by talking about why gravitational waves. Okay, now long back when I was an undergraduate, one of the physics courses I had taken during my engineering was GR, and Professor Vishweshwara had sort of made it clear to me that there's a lot of beauty in that topic, but also the other person, HS Mani, made it a precision thing. I mean, you need to be able to calculate things. So it was a very nice mix that I got in my undergraduate. So the important thing is it's beautiful, is great. The most important thing about a physical theory is it's successful. It has withstood the test of experimental things, right? So GR had matched all the experimental tests till now. And the question that Einstein asked soon, within a year of discovering general relativity, is what happens if, in general relativity, as most of you must know, that you don't have gravitation as a force like we thought of in Newton's times, but it is a manifestation of the curvature of space-time. Okay, so space curves around mass, any mass, and then that is what is. The question is what happens when you move masses, right? And Einstein answered that by saying you will have ripples which will float out. Importantly, besides the other thing, this is the major qualitative difference between Einstein's gravitation and Newton's theory. Okay, otherwise, many of the tests you could fudge Newton's law and imagine you'd fit it with a higher order term, like not just 1 over r square, but putting an 1 over r cube. And a lot of people actually spend a lot of time trying to put those terms to explain Mercury, the perihelion shift. It was talked about as the detection of the century. I'm not going over those slides because I'm sure you have seen them thousands of times. So it opened up in 2015 again, for us, because in September we knew this had happened, but the world knew about it a few months later in February after a lot of check. So we first detected gravitational waves in LIGO detectors, which are enormous 4-kilometer detector apparatus. Your Michelson interferometer on a 4-kilometer scale, right? So that's what is required to detect it. I again will not spend too much time over that. What I wanted to tell you is just like first time we started uh, seeing, and then finally, this to me is the biggest quest, and not only me, but if you hear the Nobel lecture of Revise, it's a short one. You'll find the clip somewhere. He mentions that as the next milestone discovery. This is to see the gravitational waves from the birth of the universe, near the birth of the universe. Okay, and that we believe the closest in that to prove that is the microwave background. And that's basically the area I work in. So let me start with that. So why is it interesting to see the universe in gravitational waves on cosmological scales? Okay, now what is the detector here, which is interesting? So I am sure many of you have heard talks about how LIGO detects gravitational waves, or how a Michelson interferometer works, right? It detects the change in path lengths. And if a gravitational wave goes, it just changes physical distance between the mirrors and you pick that up. Now, on cosmological scales, where is the mirror? What are you looking at? What you're looking at is in cosmology, largely because of the fact that light travels at finite speed. When I look out, I look back in time, right? So when I look out 14 gigaparsecs, which is like 43 billion light years, that's the furthest you can see electromagnetic radiation from. Because after that, the universe, because you have hit a universe that's so back in time, it's very hot, it's 3300 Kelvin, and all the matter is ionized. And you know that plasma has free electrons, so no electromagnetic signal, really coherent signal, can come past that. So it's like looking at the clouds, right? It's a opacity equal to 1. So the mean free path of photons is very small here. So this, any observer in the universe sees basically a super IMAX theater around us, and we are blessed that radiation from that comes completely unimpeded over 43 billion light years in the wave band frequencies of say 30 gigahertz to 6,000 gigahertz, right? It's just there, and that's what is the microwave background. It's just suppose that window is open to us. So you can see this, you can see patterns on it, right? Now that can be our detector. I see patterns. So there I'm showing you temperature patterns, but there's also polarization pattern. But now you imagine a gravitational wave of this scale comparable to the sphere. Okay, it's a sphere of 43 billion light years. So you look at a gravitational wave of that wavelength. Of course, if you compute the time period is cosmological. So you won't see it evolving, but you will see it as a shear field on this thing. What it will do is, oh, sorry. I'll come back to that. I think there was a mix up of the slides, but let me go to what I'm telling here. So in cosmology, the point is these fluctuations actually translate to the Laplace structure, and these fluctuations we believe were generated by some mechanism in the early universe. And the best mechanism that we have is something called inflation. And it is imperative that if that works for generating density perturbations, it must produce gravitational waves. So this is why we believe that there will be gravitational waves on this scale. Okay, so let me come back to that. And since this is inevitable, we keep drilling down with observations, and we are putting limits on this. So just to tell you that this game is from pre-WMAP, which is like 2000 onwards to now, that this thing has steadily been, no, limits on how much gravitational waves are there, but we haven't detected it yet, right? There was a claim detection in between, but we haven't detected it. But it's a must do for cosmology. And this is something that I should also point out was some part of my research. By one of my earliest papers is on gravitational waves contribution to the CMB. So this has been on my mind. So I'm really glad that at a very late stage in my career, I'm getting back to that. And this is not from this is from my first paper. So we produced the first CMB normalized predictions for the gravitational waves from the early universe. Okay, so this is like 1992. Okay, and then even there, we had put limits from Kobe, and then later I just added this WMAP and SS thing. Nevertheless, the picture is the same mechanism which creates the density fluctuations from which galaxies move, also creates, inevitably must create gravitational waves. So if we see them, that's a vindication of that early universe scenario of inflation. If we don't see them, it makes it more improbable, right? It won't rule it out completely, but it looks more improbable. Okay, and so this is the same picture saying density waves are created and gravitational waves are created, and you see them in a particular pattern on the microwave background sky, pattern of linear polarization. This is the detector, cosmic gravitational wave detector. So I already talked to you about this plasma screen, which surrounds us. And suppose you have a large wavelength thing, what it does is shears this screen. Okay, so it does this. I mean, it's of course exaggerated, but it's not too bad. I mean, it happens at the level of 10 to the minus 6. Okay, for the kind of precision things we talk about, minus 6, minus 7, depending on the level, amplitude of the gravitational waves. But we will be able to see it up to say 10 to the minus 8 deflect. Okay, so that goes back if I have this. Oh no. So that has to see, that is because of the fact that the spectral energy density is flat. Okay, so if you look at this, this is h square lambda, omega square, right? So the point is it scales up. So for the same amount of energy density, the h has to be very large. Okay, so this is an amazing part that on larger scale. So so LIGO detects delta L by L of 10 to the minus 22, right? But LISA has to detect 10 to the minus 20 because it's at lower frequency. As you go to lower frequency, it's the gravitation wave signal is for the same power is much larger. PTA is very much larger in H. Observer. But that's just a greater Lisa. So that is probably future extensions. Okay, that's a good question. But so it's not, I mean, so given that we create things at 10 to a minus 10 precision and all that, the screen is distorted at 10 to minus 8, we should see it. Okay, so what particularly happens is the cosmomicro background sky, this picture on the IMAX theater, looks something like this, much higher resolution than this in this color. But I have a low resolution one just to pinpoint that there is this linear polarization information. So you can actually draw sticks, point in any direction you look at the cosmomicro background, there is a, and with a polarizer, you'll find a direction in which the amplitude is largest, right? Which means then you say, okay, that's a polarization direction. And you keep doing that all over the sky, you'll get a pattern of sticks. Now, again, you're very smart undergraduates. So if you have a